Hello, once again, geometry students. Welcome to another week of distance learning. And I want to talk about two special right triangles. And these are special right triangles because we often use them in geometry and pre-calculus and other branches of math to set up problems where we easily know what the sides of a triangle might be. So once we figure out these two special right triangles, we'll be able to use them to solve math problems for the rest of the marking period. The first of these two special right triangles arises out of the equilateral triangle. One of the things we have to remember from equilateral triangles is the theorem that all equilateral triangles have 60-degree interior angles. So I'm going to go ahead, draw 60 degrees down there. I'm also going to label the vertices of my triangle. A, B, and C. The first thing I want to do here is I want to form a right triangle here because my special right triangles are right triangles. And one way I absolutely know how to form a right triangle is to draw an altitude of this triangle. Remember, our altitudes are line segments that connect any vertex to the opposite side and do it such that the line segment and the opposite side are perpendicular. I'm going to say for this triangle, just for the sake of argument, that our sides are 2. Okay? So I'm going to say that side's 2, that side's 2. We're not really going to care about this side of the triangle, but this side here, my AB is 2. I'm also going to label the point where the altitude touches the far side of the triangle as D. And one of the things you might remember with equilateral triangles is not only is AD an altitude, but for equilateral triangles, altitudes are also medians. So that means that this point D is halfway between B and C, which means that if the length of a side of the equilateral triangle is 2, then this length BD is going to be 1. We also know from the triangle angle sum theorem that all three of these angles, B, BDA, and DAB, have to add up to 180. Since there's 90 here already at D and 60 here at B, the remaining angle, all that's left over, is 30 degrees. So we know right now all three measures of the angles. I know two sides of the triangle, and I want to figure out what AD is equal to. And for this, since I have a right triangle, I want to use the Pythagorean theorem. So what I'm going to say here is, let's remember the hypotenuse, AB. If we square that hypotenuse, that's going to be equal to the sum of the squares of the other two sides. In this case, BD and AD. So I can plug in my values that I have here. AB is 2, and 2 squared is 4. BD is 1, and 1 squared is 1. And I'm looking for AD, so I'm going to keep that the same. I'm subtracting 1 from both sides. So AD squared is going to be equal to 3, which means that AD equals square root of 3. So this remaining side here is the square root of 3. And that there is my first right triangle. That is my 30, 60, 90 right triangle. I'm going to draw it again just by itself. I know that that's a right angle. That's 60. That's 30. The side opposite of my 30 is 1. The side opposite of my 60 is root 3. And the hypotenuse is 2. The second special triangle that we're going to work with comes out of the isosceles right triangle. So here's a right triangle that has both legs congruent to each other, and thus this is an isosceles triangle. And we can figure out the angles quickly off of this using the isosceles triangle theorem, which states that if two angles, or if two sides are congruent, then the angles opposite of those sides are also congruent. So I know that that angle and that angle are congruent. So I know both of these are 45 degrees. If I just go ahead and say that the two legs are also of length 1, I'm just going to arbitrarily say that, but it makes the math easier. Then I can figure out what the measure of the hypotenuse is going to be. So AB squared is going to be equal to AC squared, which is 1 squared, plus BC squared, which is also 1 squared, or 1. Thus, AB squared is going to be equal to root 2, or AB squared is going to be equal to 2, and thus the hypotenuse AB is going to be equal to root 2. And that's my second special triangle. We're calling it the 45, 45, 90 right triangle. And my sides are going to be 1, 1, and root 2. Root 2 being the hypotenuse. So those are my two special triangles. Now the question you're probably asking yourself is, why do we care about these triangles? And the important thing is that you have to recall that all triangles with at least two congruent angles are similar. Right? That's our angle-angle similarity postulate. And thus, by the definition of similar triangles, all sides of two similar triangles are proportional. So that means that for every 30, 60, 90 right triangle, every single one of those triangles is going to have a proportion of 1 to root 3 to 2 for its sides. Similarly, for 45, 45, 90, every single one of those triangles is going to have sides in the proportion of 1 to 1 to root 2. That means if we know a triangle is either the 30, 60, 90 right triangle or the 45, 45, 90 right triangle, and we know the length of one side of the triangle, we're going to know the length of all three sides of the triangle. This one we're given a 30, 60, 90 right triangle. And the problem asks you to find out, well, what is AC? If we do our regular 30, 60, 90 right triangle, my proportion is, my hypotenuse is my 2, my short side is my 1, and AC is my root 3. But for this triangle, my hypotenuse is 16. So I have to use my proportion again to figure out what AC is. So AC is going to be proportionate to that root 3 from the basic triangle, in the same way that BC, which is 16, is going to be in proportion to 2. Now, if I do my cross multiplication, 2AC is going to be equal to 16 root 3, and I'll divide through by 2, and thus AC is going to be equal to 8 root 3. I want to finish off by talking about applying it to the work that we've been doing so far. So question number 3 asked me, what's the perimeter of triangle ABC if A was equal to 4? So that means that we got to find AC and BC, which are both in this case, hypotenuses of triangles. And then we need to find AB, which is going to be the sum of AD and BC. So I want to start out here on this 45, 45, 90 right triangle, recognizing that A equals 4 is one leg. That means that this other leg of that triangle is also going to be 4. And then that the hypotenuse is going to be the length of the leg times the square root of 2. So CB is going to be 4 root 2. So I already know 2 out of the 4 pieces of information that I need. Now this is going to be my 30, 60, 90 right triangle. And again here, I'm given A here, which is my small side. My hypotenuse is going to be 2 times A. And this longer leg is going to be root 3 times A. And since A is 4 in this case, get rid of those A's and I'll just multiply them by 4. And thus, my diagonal is going to become, or my hypotenuse is going to become 8, and AD is 4 root 3. And now to find the perimeter, I just have to add all these together. So it's going to be 8. I'll do my other whole number, plus 4 root 2 plus 4 root 3. Add all my like terms together. 12 plus 4 root 2 plus 4 root 3. If you plug that into a calculator, that's going to give you a value of 12 plus 4 root 2 plus 4 root 3. And that will come out to be about 24.59. So that's what our perimeter is going to be. So using our special right triangles, we're able to take just the height, just the altitude of this triangle, and knowing that those two interior angles are 30 and 45, figure out what all 3 sides of the triangle is. We are given here a parallelogram, and we're asked to find what's the area of this parallelogram. We're going to remember from our last unit, area of a parallelogram is base times height. But here we're not given the height directly. Instead, we're given the value of this other side. Right? We're given just the lengths of the sides. So I'm going to go ahead, I'm going to choose this 26 as my base. I'm going to say that's 26 times. And then I'm going to go and use this other side, this 22, as the hypotenuse of a 45-45 right triangle. And I know that this 22 then is going to be in proportion to root 2, right? Because for my 45-45, it's root 2, 1, and 1. So I know that that 22 is going to be proportional to that root 2 the same way as my height is going to be in proportion to 1. So that means that height is equal to 22 root 2. Remember, we're not barbarians in this class. We don't leave square roots in the denominator. We have to simplify this. So I'm going to do that by multiplying top and bottom by that root 2. Right? Essentially what I'm doing here, I'm multiplying through by 1. That's going to allow me to now have 22 root 2. And if I multiply my root 2 by my root 2, that's going to get me a 2. I'll cancel out my 2, divide through with the 22, and that's going to get me a height of 11 root 2. I'll bring that back up to my formula. That's going to be 26 times 11 root 2. And plugging that into a calculator will get us an area of approximately 400.47 square inches. All right, give the practice problems that I've put up on Google Classroom a try and ask any questions that you have during office hours. Good luck.